Welcome to Aerodynamics of Flight Part 2, where we will discuss turns, slow flight, load factor, ground effect, and induced drag. Let's begin with level turns. In level flight, the vertical component of lift opposes weight. In order to change the plane's direction of flight, the wings are banked and the total lift vector is divided into separate vertical and horizontal components. It is the horizontal component of lift which causes the airplane to turn and is also responsible for the increased load factor, which is defined as lift divided by the airplane's actual weight. Notice as we bank the airplane 30 degrees, the vertical component decreases, the horizontal component increases, yet the total lift vector remains the same. In this condition, the airplane will necessarily begin a descent as the vertical component, producing 1,732 pounds, can no longer support the weight of the airplane, which is 2,000 pounds. To counteract the loss of vertical lift, the angle of attack must be increased. In a level 45-degree turn, the g-force created is given as 1 over cosine 45, which is 1.4142. Therefore, in a 45-degree bank, the plane would effectively weigh 2,828 pounds, and the occupants would feel about 40% heavier compared with level flight. This G-loading results from applying back pressure to the yoke to increase the angle of attack in order to produce the necessary coefficient of lift to oppose this heavier flight condition. On the other hand, if we were to allow the plane to descend in the turn, the G-loading would be less or even zero. Note when the horizontal component of lift and/or centripetal force and the centrifugal force are equal in magnitude, the plane is said to be in coordinated flight. So how do we keep an airplane in coordinated flight? We use the rudder. In the first panel, we see an example of coordinated flight where the horizontal component of lift and centrifugal force are balanced. A slip is where the angle of bank is too steep for the rate of turn and the nose of the airplane points to the outside of the turn. The horizontal component of lift is greater than the centrifugal force. Conversely, a skid is where the rate of turn is too fast for the angle of bank and the nose points to the inside of the turn. That is, centrifugal force is greater than the horizontal component of lift. Not all slips are bad. In fact, they can be used effectively to manage crosswind landings and descend quickly without increasing airspeed. Skids, however, are to be avoided, and more on that later. So why does banking an airplane lead to uncoordinated flight? The answer is adverse yaw. Whenever a wing produces lift, there is a byproduct called induced drag. In this illustration, you see the airplane banked towards the left. This is accomplished with a downward deflection of the right aileron and upward deflection of the left aileron. This effectively increases lift on the right wing and decreases lift on the left wing. As a result, there is asymmetric drag. On this graph, we can again see the relationship between lift and drag, and that as you increase angle of attack, you simultaneously increase induced drag. At higher angles of attack, this drag increases exponentially. In a left turn, the aileron on the right wing is deflected downward, while the opposite occurs on the left wing. This results in lift on the right wing, rolling the airplane to the left, while simultaneously reducing the lift on the left wing. The increased lift produced by the right wing creates induced drag, which rotates the airplane along its vertical axis in a clockwise direction when viewed from above, and the nose of the airplane becomes pointed to the outside of the radius of the turn, creating a slip. To correct this condition, inside rudder should be used. Conversely, in a left turn with excessive left rudder input, the plane will skid as centrifugal force is greater than the horizontal component of lift. To correct this, lighten the rudder pressure on the left pedal or add a little outside rudder pressure. When initiating a turn, only add enough rudder input to combat adverse yaw and keep the plane coordinated. Too much rudder pressure can result in a skidding turn, which should be avoided. In a skidding turn, the nose points to the inside of the turn and the empennage slides to the outside. The turn coordinator shows the ball being thrown to the outside of the turn, indicating greater centrifugal force than is needed for the angle of bank. To correct this, step on the ball in order to yaw the plane into coordinated flight. In coordinated flight, the centrifugal force and horizontal component of lift are balanced, and the nose and tail of the airplane are aligned along the curved path of the turn. In a slipping turn, the horizontal component of lift is greater than the centrifugal force, so the nose points to the outside of the turn and the empennage toward the inside of the turn. To correct this, again, step on the ball, which has fallen to the inside of the turn. By applying adequate rudder, the nose will yaw towards the inside of the turn, re-establishing coordinated flight. There are several things to consider when executing a steep turn. 1. As angle of bank increases and or airspeed decreases, the radius of turn decreases. The opposite is also true. 2. When rolling into a turn, there will be gradual loss of the vertical component of lift, which will require the addition of elevated back pressure to increase the angle of attack. 3. The byproduct of increased angle of attack is induced drag, which steals energy from the airplane. In order to avoid decelerating and losing altitude, additional power must be applied to rebalance the forces. 4. In a steep turn, there is a tendency for the outside wing to overbank since it is traveling faster compared with the inside wing and therefore producing more lift. As a result, some opposite aileron may be necessary. 5. Larger amounts of adverse yaw and left turning tendencies should be expected, especially with turns to the right. And finally 6. Due to increased load factor, there will be increase in stall speed. Let's examine some of these in more detail. When in a steep turn, the outside wing has an increased velocity relative to the inside wing. The faster a wing travels through the air, the more lift it produces, which accounts for the overbanking tendency during a steep turn. Next, let's talk about load factor and angle of bank. Load factor is defined as the ratio of lift over weight and often uses the term Gs. It is a measure of stress imposed on the aircraft during various flight maneuvers. In straight and level flight, the load factor is 1, as lift and weight are equal and opposite. In a level turn, the total lift vector is redirected at some angle theta, and there is an opposing vector which must be equally balanced. Tilting the lift vector introduces a center-seeking or centripetal force, also referred to as the horizontal component of lift, as well as the perceived equal and opposite center-fleeing or centrifugal force, which passengers, pilots, and plane experience. Using trigonometry, we find that cosine of theta is equal to weight, or mass times gravity, over lift. If we take the inverse of this relationship, we find that 1 over cosine theta equals lift over weight, which is in fact the definition of load factor. Therefore, an airplane in a level turn experiences a load factor which is given simply by 1 over cosine of the angle. Notice on this spreadsheet how steeper turns lead to greater load factors, which increase exponentially with larger bank angles. Let's see how load factor and stall speed are related. Here is a graphical plot of load factor versus bank angle in a level turn. Here is the same information with percent stall speed increase versus bank angle included as well. On the previous slide, we saw how load factor in a level bank turn is calculated as 1 over cosine the angle. So for example, in a 60-degree level bank turn, the load factor is 1 divided by cosine of 60, or 2. The increase in stall speed is proportional to the square root of the load factor, which for a 60-degree bank is 1.414. Therefore, the stall speed will increase by 41%. The next relationship we'll discuss is that of rate of turn and radius of turn. At a constant airspeed, the larger the angle of bank, the smaller the radius of turn, and the greater the turn rate. Now for a constant angle of bank, the slower the airspeed, the smaller the turn radius, and the greater the rate of turn. The next slide will go into detail why this is the case. Using the same diagram from our discussion for load factor, we can derive the equation for how bank angle and velocity affect radius of a turn. The centripetal force is equal to the mass times velocity squared divided by the radius. Using trigonometry again, we can show tan theta is equal to sine of the angle divided by cosine of the angle. Simplifying the equation, tan theta equals velocity squared divided by radius times g. Isolating radius, we find the relationship that radius of a turn is equal to velocity squared divided by g multiplied by tan of the angle. Or said differently, for a given bank angle, as velocity increases, the radius of turn increases. Conversely, if the velocity is held constant, a larger bank angle will result in a smaller radius of turn. Finally, let's discuss performing a steep turn. After clearing turns are completed, and the airplane is trimmed for level flight at the airspeed per manufacturer's recommendation, or maneuvering airspeed, begin to roll into a coordinated turn for a count of about 5 seconds. Don't rush to get to 45 degrees. As you roll through 30-degree bank, you'll need to begin adding back pressure to maintain level flight. Remember, you will require more right rudder when turning to the right due to left turning tendencies and adverse yaw. For left turns, less rudder will be needed, or perhaps none at all. Increasing back pressure to provide lift will also increase induced drag and slow the airplane. Therefore, anticipate adding 100 to 200 RPMs of power. Trim is optional. Pick a spot on the cowling or glare shield which you can use to trace the horizon as you turn. Closing one eye can help you keep the reference point and the horizon aligned. Watch for upward or downward deviations of the horizon from your reference point. Remember to spend most of your time looking outside and only glancing inside at the instruments to get the relevant data and return to the visual references. If you are losing altitude during the turn, first try decreasing the bank angle to restore some of the vertical component of lift. If that doesn't correct your altitude, you may also try adding some back pressure to the elevator. Conversely, if you are climbing in a turn, try first to steepen the bank angle to reduce the vertical component of lift. You may also try reducing the back pressure on the elevator. Finally, roll out the number of degrees equal to half the bank angle. So for example, a 45-degree bank, you would roll out between 20 to 25 degrees short of your initial heading. Then repeat the maneuver in the opposite direction. Slow flight is designed to familiarize the pilot with the airplane's flight characteristics at the low end of its envelope, where the behavior is somewhat counterintuitive. In the region of normal command at a constant altitude, increase in power results in increased airspeed. In other words, more power is required to overcome parasitic drag, which predominates in this region. Conversely, in the region of reverse command at a constant altitude, decreases in airspeed require increases in power. That is, more power is required to overcome the increasing induced drag as the airplane slows. Regardless of which side of the power curve you find yourself, the elevator alters pitch and thus airspeed. So for instance, pitching up will slow the aircraft as it climbs, and conversely, pitching down will increase airspeed. The throttle provides power and thus increases total energy to the airplane. For a constant airspeed, increasing power will cause the aircraft to gain altitude, and conversely, reducing power will cause the aircraft to lose altitude. Let's dive in. Let's talk about slow flight, or operating in the region of reverse command. The L/D curve describes the effect of induced and parasitic drag on an airplane at varying air speeds. At the bottom of the curve is our best glide speed. When we're talking about total drag, we're also referring to the thrust required to maintain a specific airspeed. Above the airspeed associated with LD max, parasitic drag predominates as induced drag decreases. Below this airspeed, induced drag plays a greater role in the total drag as parasitic drag falls off. Parasitic drag varies directly with velocity squared, whereas induced drag varies inversely. Note, Vmax endurance occurs at a velocity slightly less than L over D max and represents the division between the front side and the back side of the power curve. Now suppose you are flying along trimmed for level flight on the front side of the power curve, and a wind gust caused the nose to pitch up. What would happen? Well, the airplane would momentarily slow down, but if there was no change in the power setting, would it return to its original speed? When operating on the front side of the power curve, as airspeed slows, total drag decreases mostly due to less parasitic drag. Since power hasn't changed, but total drag has decreased, there is excess power available. The airplane will then seek its previous airspeed. This behavior is termed speed stable. Next, what would happen if you were trimmed for level flight, flying on the back side of the power curve, and a wind gust caused the nose to pitch up? As we saw in the previous slide, the airplane would momentarily slow down, but if there was no change in the power setting, would it return to its original speed as it did in the case for the front side of the power curve? It would not. In the region of reverse command, or back side of the power curve, as airspeed decreases, total drag increases primarily due to induced drag. Since the power setting is less than that required to overcome this new total drag, the airspeed would continue to decline unless there was some reaction by the pilot. This behavior is termed speed unstable. Now let's look at a practical example from Bill Kirshner's book, The Flight Instructor's Manual. Suppose the airplane is well on the back side of the power curve and just about to touch down when a cow or car moves onto the runway. After the pilot opens the throttle all the way, they have to move the wheel or stick forward in order to climb. If they keep the wheel back at the near stall condition, the lack of excess power will not allow them to climb. The best rate of climb speed for this example is 80 knots, and they have to push the wheel forward to get that value. Now look at the animation which illustrates the same idea. Performing slow flight. In the most recent airplane flying handbook, they propose replacing the old adage of pitch for airspeed and power for altitude with pitch plus power controls energy state. More on that in our energy lecture. As you enter slow flight and flaps are added or retracted, anticipate pitch changes and associated changes in lift. Remember, it is very important to remain coordinated in slow flight, so in the event a stall occurs, it minimizes the chance of entering a spin. At high angles of attack, your horizon reference over the cowling may be obscured. Scan left and right and at your Lindbergh reference for traffic and visual clues as to the airplane's condition. The Lindbergh reference refers to an area where the windscreen and glare shield intersect and permits off-center viewing of the horizon when straight-ahead visualization of the horizon is not practicable. At slow airspeeds, the ailerons and elevators feel sluggish and are less effective because of less airflow. The rudder, being the largest control surface, is the most effective surface for maintaining directional control. When operating deep in the region of reverse command and approaching a stall warning, lower the nose to regain airspeed, but also add power to maintain altitude. Flying on the back side of the power curve will result in high angles of attack and require high throttle settings similar to those during takeoff. There will also be considerable left-turning tendencies, which will need appropriate rudder input to be neutralized. Turns in slow flight should be very shallow and not more than 10 degrees to avoid excessive load factors which would increase the stall speed. Finally, to exit slow flight, lower the nose, add power, and gradually retract flaps and resume straight and level flight. Our final discussion for this presentation will be on ground effect. Ground effect occurs due to the Earth's surface interfering with the airflow around the wings, resulting in decreased induced drag and consequentially increasing the vertical component of lift. This has implications for both takeoff and landing phases of flight. Let's begin. Wingtip vortices are created by high pressure along the undersurface of the wing, traveling outward toward the wing tips until it reaches a low pressure on the top side of the wing, resulting in a spiral stream which rotates, creating a whirling mass of air, trailing behind the airplane as it continues to move forward. These vortices are also deflected downward, which increases induced drag and thereby decreases the vertical component of lift. Note how the vertical component of lift increases as the airplane goes from a high angle of attack to a cruise-type configuration. Wing vortices and the wake turbulence they create are most pronounced when the airplane is heavy, clean, and slow, or conditions requiring high angles of attack. Let's begin with some definitions. The spanwise vector is the airflow which parallels the wing's surface along the span of the wing and degrades lift. The chordwise vector is the airflow which is perpendicular to the wing chord and promotes lift, and the blue line represents the resultant airflow. In cruise flight, the angle of attack is small and the airspeed is large. This accounts for the small spanwise vector compared to the larger chordwise vector. In the next slide, we will see what happens when we enter slow flight and there is a large angle of attack and decreased airspeed. In slow flight, there is lengthening of the spanwise vector due to increased wingtip vortices and shortening of the chordwise vector secondary to reduced airspeed. This creates greater and greater amounts of induced drag. Next, we will see how ground effect interferes with these wingtip vortices, thereby reducing induced drag. Ground effect is the phenomena of improved lift which begins about one wingspan height above the ground. This occurs by the ground interfering with the wingtip vortices and thus spanwise flow. As a general rule, the lower the wing can get relative to the ground, the more pronounced the effect on induced drag. Let's compare two airplanes. For example, a Cessna with its wing 7 feet above ground and wingspan of 36 feet versus an Archer with its wing 3.5 feet above the ground and wingspan of 35 feet. When the high-wing airplane is just about to touch down, it will be at about 20% of its wingspan's length above the ground and will experience 60% of its normal induced drag. Stated another way, it will have a 40% reduction of its normal induced drag. When the low-wing plane is just about to touch down, it will be about 10% of its wingspan length above the ground, resulting in 40% of its induced drag, or a 60% decrease from normal. As a result of these different wing configurations, low-wing airplanes tend to float more in ground effect compared with high-wing. Let's explore a few more consequences when flying in ground effect. First, due to the decreased induced drag when in ground effect, the thrust required to achieve a given airspeed is less compared to when the plane is flying above ground effect. Second, when in ground effect, the coefficient of lift is greater for a given angle of attack compared to when the airplane is out of ground effect. From a practical standpoint, the airplane can become airborne at a lower airspeed. However, if it climbs above ground effect, the coefficient of lift may decrease due to sudden increase in induced drag, and the airplane may settle back on the runway. To solve this problem, rotate at the manufacturer's recommended airspeed, or, in the case of a soft field takeoff, lift off at a lower airspeed, but remain in ground effect until you build up sufficient airspeed to begin the climb. In summary, when the airplane enters ground effect, the rearward directed induced drag decreases due to interference by the ground with the wingtip vortices. This gradually tilts the total lift vector forward, increasing the vertical component of lift. For the same angle of attack, as the plane flies deeper into ground effect, the vertical component of lift continues to get larger as the induced drag becomes smaller. Finally, as the plane slows, lift gradually decreases and the plane sinks. The pilot responds by increasing the angle of attack to slow the rate of descent until the wings reach their critical angle of attack and the airplane stalls at the point of touchdown. Thanks for joining us today, and remember, fly smart and stay safe.